Today we are going to be working with van der Waals' equation of state. And if you're not familiar with what an equation of state is, it's basically a relationship between three thermodynamic variables of a compound: the pressure, specific volume, and temperature. So we can already kind of model this relationship by using the ideal gas law, which we have worked with a lot on my channel. And we know that to be the pressure times the volume is equal to the number of moles times the ideal gas constant times the temperature. So I'm going to write that. But for what we want to do today, we're actually going to set the amount or the number of moles equal to 1 so that PV equals RT. And it's also worth mentioning that in this state, the volume is equal to cubic meters per mole. So we can actually rearrange this equation further so that PV divided by RT is equal to 1. And this equation is going to be useful later, so we're going to come back to this. So in the ideal gas law, the behavior of a gas is modeled such that it is under idealized conditions. The consideration of the interaction or the attraction between other molecules is not present. And we know this to not really be very realistic. We do know that gases will be attracted to other molecules and they will interact with other molecules. So we have to account for this in our present equation of state. So we're first going to rewrite it to solve explicitly for the pressure. So P times R times the temperature divided by V. And we know that when molecules or atoms start to acknowledge each other, and once they start to become more present within the container, well, there's going to be less space and room for other atoms. So we're going to account for that in our equation of state by subtracting a term that we'll call B. So another thing that the ideal gas law does not account for is, as I mentioned, the attraction between molecules. And we know that regardless of how polar or nonpolar a molecule is, there will always be an attraction to other atoms or molecules. And we know of attractions such as the van der Waals forces, hydrogen bonding, ion-ion interactions, dipole-dipole interactions, so on and so forth. So we are going to subtract a term called A and divide it by the volume squared. So by incorporating all of these factors into our equation of state, we have actually achieved van der Waals' equation of state. So what does this look like? You know, what are these A and B terms? We're going to cover that in this video. So if we were to graph this equation, it would very roughly, and I mean very roughly, you know, I have to give the disclaimer, I'm not an artist. It would very roughly look something like this. I will put a link to the actual graph, the actual pressure versus volume graph, so you can have a better understanding of what this relationship looks like. But you'll notice that there are some inflection points of this graph that basically make it go from concave up to concave down. And so we will be able to take the first and second derivatives of this equation at those points. So we can go ahead and write our first and second derivatives for the van der Waals equation of state, such that the derivative of the pressure with respect to the specific volume is negative R times the temperature divided by the volume minus B squared plus 2A divided by the volume cubed. And that the second derivative of the pressure with respect to the specific volume is equal to 2R times the temperature divided by the volume minus B cubed minus 6A divided by the volume to the fourth power. So I brought up the question of how would we find A and B, and you could probably assume that all we would have to do is to set these two equations equal to 0 and find the roots of those equations, and then we'll have the values for our A and B terms. But this is a mistake. If we were to simply do that, we would basically be saying that the derivative of the pressure with respect to the volume is 0, and that looks something like this. And we know this not to be true. So what we really have to do is be very careful and make sure that we are evaluating the derivatives at our critical values of a compound. So we can actually erase these equations and evaluate each at the critical temperature, critical pressure, and critical volume. And rewrite the equations and incorporate each of those values. So this equation becomes negative R times the critical temperature divided by the critical volume minus B squared plus 2A divided by the critical volume cubed, and 2R times the critical temperature divided by the critical volume minus B cubed minus 6A divided by the critical volume to the fourth. And we can set these equations equal to 0 and solve for our A and B terms. So now that we've done that, I will go ahead and subtract this term to the right and add this term to the right, so that we are left with negative R times the critical temperature divided by the critical volume minus B squared is equal to negative 2A divided by the critical volume cubed. And before we move on to the next equation, I will go ahead and do some basic algebra here. Clearly we have some negatives on both sides, so we can go ahead and make those both positive. And then we can move on to our second equation that says 2R times the critical temperature divided by the critical volume minus B cubed equals 6A divided by the critical volume to the fourth. And we can do some algebra here as well, because we have a factor of 2 in each of our numbers. So I'll go ahead and erase this 2 and erase this 6 and turn it into a 3. So the next step that we're going to take from here is actually take our first equation and multiply it by the reciprocal of the second equation on both sides. So at first, we get that R times the critical temperature divided by the critical volume minus B squared is multiplied by the reciprocal of the term on the right of our second equation. So the critical volume minus B cubed divided by R times the critical temperature. And again, I'm going to go ahead and make these modifications now before moving on to the second side. So we can clearly see that our R times the critical temperature terms will cancel out. And we have this entire term canceling out, and this power of our critical volume minus B term reducing to 1. And so we can set that equal to 2A divided by the critical volume cubed times the reciprocal of the term on the right side of our second equation, which is the critical volume to the fourth divided by 3A. So we can do some more algebra here and see that our A terms cancel out. This entire critical volume cube term cancels out, and we're left with a critical volume to the first power in the numerator. So now we can write the raw form of this equation after we've done all the multiplication and algebra, so that we get the critical volume minus B is equal to 2/3 of the critical volume. So now we can go ahead and solve for B, and what I'm going to do is factor out a negative from both sides so that B is positive and the critical volume on the left is negative, and then I'm going to add the critical volume to the right side so that B is equal to negative 2/3 of the critical volume plus the critical volume. And if this is negative 2/3 of the critical volume, then this becomes 3/3 of the critical volume, which leaves us with 1/3 the critical volume. And that is our equation for B. So now that we have B, we can go ahead and solve for A. So we're actually going to use this first equation, since they're already, our terms are already set equal to each other. And I'm just simply going to flip it so that the term with 2A in it is on the left side. So 2A divided by the critical volume cubed is equal to R times the critical temperature divided by the critical volume minus B squared. So since we know that B is 1/3 of the critical volume, we can go ahead and substitute that in. And the basic algebra that we just did would simply state that this term is equal to 2/3 of the critical volume, but that term is squared, so we'll end up getting that R times the critical temperature is divided by 4/9 of the critical volume squared. And we know when there's a fraction in the denominator, we just multiply that by the reciprocal. So then we'll have 2A divided by the critical volume cubed is equal to 9R times the critical temperature divided by 4 times the critical volume squared. So from here, all we really have to do is isolate our A term, which simply means multiplying both sides by the critical volume cubed and dividing both sides by 2, so that A is equal to 9/8 R times the critical temperature times the critical volume. And so now we have both A and B terms. And since we have both of those terms, this enables us to come back to our van der Waals equation of state and input what those A and B terms are. But we have to remember that we are, evaluating these at the critical value, so our pressure also has to be critical pressure in this scenario. So we can rewrite this so that the critical pressure is equal to R times the critical temperature divided by the critical volume minus B, but we know B to be 1/3 of the critical volume, minus A, which we know to be 9/8 R times the critical temperature times the critical volume divided by the critical volume squared. And so again, all we really have to do is algebra here. This becomes R times the critical temperature divided by 2/3 the critical volume minus 9R times the critical temperature times the critical volume divided by 8 critical volume squared. And this further simplifies to 3R times the critical temperature divided by 2 times the critical volume minus 9R times the critical temperature divided by 8 the critical volume. And so clearly we're not done because these fractions have a common denominator of 8 or 8 times the critical volume. So we can multiply this term by 4/4 and get that the critical pressure is equal to 12/8 minus 9/8 R times the critical temperature divided by the critical volume, so that the critical pressure is truly equal to 3 times R times the critical temperature divided by 8 times the critical volume. And so you'll notice that, well, hey, we have a relationship between critical pressure, critical temperature, and critical volume. And at the beginning, we had a similar relationship using the ideal gas law, such that PV divided by RT was 1. Well, we can rearrange this equation such that the critical pressure is equal to 12/8 minus 9/8 times R times the critical temperature divided by the critical volume, so that the critical pressure is truly equal to 3 times R times the critical temperature divided by 8 times the critical volume. And so you might take note of the relationship here that we've displayed between our pressure, temperature, and volume, which is what we did at the beginning with the ideal gas law, stating that PV divided by RT is equal to 1. Well, we can rearrange this equation so that the critical pressure times the critical volume divided by R times the critical temperature is equal to 3/8. And so what's really cool about this is that this is known as something called the compressibility factor. Known as Z. And what the compressibility factor explains to us is that when a gas is at its critical values under non-ideal conditions, it behaves 3/8 or like 37-38% of how it behaves under ideal conditions. And so, you know, when you learn a lot about the ideal gas law and how gases behave under ideal conditions, you never really get to see how they behave under non-ideal conditions until you work with something such as the van der Waals equation of state. And the two equations are pretty much basically really opposite of each other, because the ideal gas law doesn't account for the interactions and attraction between molecules, whereas the van der Waals equation of state does, and you can see to what degree a gas will deviate from its ideal gas behavior under more realistic conditions. So I think that's pretty cool. So using this equation, if we know our critical temperature and critical pressure of a gas, we can rearrange this equation to solve for the critical volume of a gas, where the critical volume is equal to 3 times R times the critical temperature divided by 8 times the critical pressure. And so, hey, if we know the critical volume, then we can put this back into our A and B variables. So we know that A is equal to 9/8 R times the critical temperature times the critical volume. B is equal to 1/3 of the critical volume, and the critical volume is equal to 3 R times the critical temperature divided by 8 times the critical pressure. So we can go ahead and input our critical volume into our A and B terms. So again, A is equal to 9/8 times R times the critical temperature times the critical volume, which is 3/8 R times the critical temperature divided by the critical pressure. So that our A term is really equal to 27 times R squared times the critical temperature squared divided by 64 times the critical pressure. And we can do the same for our B term, which will be much more simple, where B is equal to 1/3 of the critical volume, which is equal to 3 times R times the critical temperature divided by 8 times the critical pressure. These 3's will cancel out, so B is equal to R times the critical temperature divided by 8 times the critical pressure. And so, knowing that this is what our A and B terms are, we no longer have the critical volume, which we didn't know, but we do have ideal gas constant, which we know, critical temperature and critical pressure, which we know as well, and simple numerical values. So if we input all of these values into the variables for A and B, we'll basically get numbers. And what's good about this is that if A and B are just numbers, then when we come back to the van der Waals equation of state, we're saying, hey, we have some volume, which will be a number, and we're going to subtract some number, and what are we going to get? Just some numerical value. And the same thing goes for A. So the cool thing about that is we've essentially done all of the derivation for A and B to be able to get to a point where we can kind of make the van der Waals equation of state kind of behave in a similar fashion to the ideal gas law. So we have successfully derived van der Waals equation of state, and we're able to retrieve the A and B terms as well as the compressibility factor, which all have allowed us to calculate more accurate thermodynamic values of a gas, and also further examine and understand the true behavior of a gas under non-ideal conditions. I really hope you enjoyed this video, and I will see you next time.